Hey everybody, this is Mr. Godfrey. Today we are going to be talking about physical properties of matter. So physical properties, that's a topic that you're probably familiar with if you actually read the last reading assignment that I gave to you guys last week and answered the discussion questions which were due today. So it's really important that you guys not only understand what physical properties are, but that you also know how to talk about these physical properties. Because when you get to college, I want you to be able to talk to smart people about physical properties so you don't sound like this.
What about the chip?
Or even worse, this. So make it your goal today to not sound like that guy, because nobody wants to sound like that guy. So the first physical property that I want to talk about is viscosity. So viscosity is a word that's defined by our textbooks to be the tendency of a liquid to keep from flowing. So it's its resistance to flowing. So in other words, you could say that the higher the viscosity, the slower the liquid moves. I usually think about viscosity in terms of thickness. So if you look at all the materials or the liquids on this slide, we have honey, we have peanut butter, we have maple syrup, and we have water. So you should ask yourself, when you're trying to determine the viscosity, you should ask yourself, how thick is, say, water? How thick is maple syrup? How thick is peanut butter? And how thick is honey? So the thicker the material, the higher its viscosity. But you need to remember that viscosity is not a constant when we're talking about a material. In fact, viscosity can change based off of temperature. Watch the following video of a marble being dropped through honey at different temperatures and answer the questions as you go. I've tried to make this as interactive as possible. Now, you will need the stopwatch that is on your table, so get your stopwatch ready and follow the directions as you watch the video. Another physical property that we need to talk about is conductivity, which is a material's ability to allow heat to flow. Now, you usually think about conductivity in terms of electricity, which is really important, and it is related to how heat flows through the material. So it's very important that you have a basic understanding of conductivity so this doesn't happen to you.
You just plug it right into the electrical.
Because believe me, you don't want to be the next YouTube viral sensation because you didn't understand what a conductive material was. Now, metals like copper wire or gold or silver are typically said to have a high conductivity. These materials allow heat to flow very easily. But there are other materials that we call insulators, like wood. These do not allow heat to flow very easily, so these are low in conductivity. Now, materials like copper wire that are high in conductivity are usually used to transmit electricity, which is something that is ubiquitous in our society today. Electricity is everywhere. You walk into a room and you automatically reach over for the light switch. If it's dark, you're immediately looking for electricity that's built into the walls. However, you'll notice that no wires are ever made out of wood, because wood is not a good conductor of electricity. But keep in mind that conductivity is defined as a material's ability to allow heat to flow, which this property has led to misconceptions about temperatures of various objects. So watch this video and just pay attention to how these people react when they find out that two materials that actually feel like they're different temperatures are actually the same temperature.
When you touch an object and it feels warm or cold, what is that really telling you about the object? Here I have a metal hard drive and a book, and I'm going to ask people to compare their temperatures. Which one do you think will feel warmer, the book or the hard drive?
The temperatures.
Yeah, tell me if one is hotter or colder, or if they're the same temperature. How do they feel?
This is slightly cooler than this one.
Yeah. Oh, that's warmer. Yeah, way warmer.
Yeah, agreed.
I'd say the hard drive is a lot colder than the book. I don't know, because the book's got more knowledge.
Why do you think that is?
Metal's normally a little bit chillier if you leave it in a colder temperature.
Well, what if I said that they're both at the same temperature? What would you say?
So you're lying.
But really?
I think you're lying, yeah.
Oh, jeez. Well, maybe the way I could prove it is I have an infrared thermometer. What do you think we're going to see?
I think science might be able to answer that, and I'm not a scientist.
Make a prediction for me.
I still think that's cool, though.
Would you bet me money?
I don't, because I don't have any cash, so yeah.
Let's measure the temperature of the book.
Okay.
What do you see?
19.0.
Okay. We measure the temperature of that.
19.0. All right, well, now I believe you.
I'm trying to actually figure it out, trying to figure out why they would be the same temperature. They don't feel the same temperature, though.
So why does that feel colder if they're basically the same temperature?
Good one. You got the answer?
Well, I'm coming to you guys for answers.
We're creatives, not intellectuals.
Well, create an answer for me.
I'm not a scientist. Come on, you tell me.
Well, I'll try to answer that question with another little experiment. Here is an aluminium block and
Ooh, nice and cold.
a plastic block.
Yeah.
How do their temperatures compare?
Completely different. Completely different.
Much colder.
Yeah.
Yeah?
Yeah, this actually feels colder.
Let's take this to the next level. I'm gonna put an ice cube on both plates. What are we gonna see?
Well, I'm guessing it would stay solid on this one and melt on this one.
So it's going to melt on the plastic but stay solid on the aluminium.
Yes, but maybe I'm wrong.
That one will melt more quickly than on the aluminium block.
You would think so. I mean, they're colder.
Yeah, because it's cold.
Let's
And
actually.
I think they're going to go the same.
All right, so we put an ice cube on each of those blocks.
Wow.
What are you seeing?
Well, it is melting a lot quicker on the aluminium.
I got it melting.
This is melting quicker than that one, even though this is aluminium, that's plastic.
So which one felt colder?
That
This
one.
one.
How does that make any sense?
I have no idea, you know.
Could aluminium be bad for the environment?
How would aluminium be bad for the environment?
Well, it's thawing out the ice a lot quicker, isn't it?
So you want the answer?
Yes, please, please.
It's about thermal conductivity, right? The rate at which heat is transferred from one object to another. So when you felt these blocks originally, I know this one felt a lot colder.
Yeah.
But you know from the other example we did that they must both be at the same temperature.
True.
Because they've both been outside for a while. We see that the aluminium block is melting the ice faster than the plastic block because it's conducting the heat to the ice cube faster.
Okay.
With the plastic block, it's a worse thermal conductor, so heat is being transferred less quickly to this ice block, and so it's staying ice.
Okay. I believe you.
Make sense?
Yes, definitely.
You know, in our first example, the hard drive felt colder even though it was at the same temperature roughly as the book. And that's because the aluminium conducts heat away from your hand faster than the book conducts heat away from your hand.
Sure, that seems logical.
Which makes the hard drive feel colder,
yeah.
and the book feel warmer.
Yes.
So when you touch something, you don't actually feel temperature. You feel the rate at which heat is conducted either towards or away from you. Think about this next time you hop out of the shower in winter. It's much nicer to stand on the bath mat than on the tile beside it. Not because the bath mat is warmer, but because it conducts heat less quickly away from you.
The next physical property that we need to discuss is malleability, which is defined as our textbooks as the ability of a solid to be hammered without shattering. So something like glass has a low malleability, because if we were to hit it with a hammer or with a baseball, you know that this glass is just going to shatter into a lot of pieces. So we would say the malleability of glass is very low. However, there are other materials like gold that can be hammered and molded and bent very easily into different shapes. So we would say something like gold has a very high malleability. Now watch this short video clip of gold, which is considered to be the most malleable of all metals.
Gold is the softest and most malleable metal. It can be pressed extremely thin, crafted into various shapes, even drawn out to form a fine wire, and all without breaking. Gold isn't affected by water or oxygen as many metals are, so it doesn't rust or tarnish either. Most gold comes from lode deposits, also called vein deposits, concentrations of gold and other metals in the cracks of rocks. Lode deposits require hard rock mining, the process of removing gold-bearing rock, called ore, by drilling and blasting. Miners descend more than half a kilometer underground. There, they drill holes for explosives using what's called a long-hole air drill. They drill in a specific pattern set out in a plan prepared by the mine's engineers. The engineers know exactly where those veins of gold are, thanks to the mining company's geologists who've studied ore samples. The company collects these samples by drilling deep into the rock at 15-meter intervals. These diamond drill cores, as they're called, are up to 100 meters long and measure 3.5 centimeters in diameter. Gold in its natural state isn't pure. It's usually intertwined with silver and other metals, so the mined ore has to be processed afterward to isolate and extract the gold. A metric ton of ore yields only about 6.5 grams of gold. After blasting the rock apart with explosives, miners use what's called a muck machine to transfer the ore to cars headed to the main shaft and then above ground to the mill. There, a crusher reduces the large chunks into smaller rocks about the size of road gravel. A mill then pulverizes them to the texture of beach sand. The factory adds a water and cyanide solution, then another mill grinds it further into a mud-like pulp. The pulp flows into large settling tanks. The wet solids, being heavier, sink to the bottom. The water at the top drains to another area. They transfer the wet solids to an agitation tank and blow in air. The oxygen sets off a chemical reaction between the cyanide and the gold trapped in the ore, triggering the gold to dissolve and leach into the surrounding water. Drum filters then separate the water from the solids. This water now joins the water that was separated earlier. They pour in zinc powder to solidify the dissolved gold and form pieces containing both zinc and gold. To smelt it into bars, they first have to mix several chemicals: manganese dioxide, fluorite, silica flour, borax, and sodium nitrate. This chemical mix, called flux, will separate the gold from the impurities. They pour it into the smelter, whose temperature is a fiery 1600 degrees Celsius. They rotate the smelter so that the contents heat evenly. Over 2.5 hours, the heavier gold eventually sinks to the bottom, while the impurities, called slag, float to the surface. They pour out the slag, taking a sample to make sure it contains no gold. If it does, it goes back in until it's gold-free. By now, the gold has cooled slightly, so they reheat to 1600 degrees Celsius, then cast into bar-shaped molds. The gold takes about 4 minutes to solidify, then another hour to cool completely in a basin of cold water. They extract the gold bars from the molds and clean off any slag residue. Gold bars are also called ingots. At this stage, the gold is 80% pure. The Royal Canadian Mint will refine it to 99.9%, the international gold standard.
The next physical property that we need to talk about is hardness, which literally describes how hard an object is. But the best way to think about hardness, it's a way of comparing different materials. So one way to compare the hardness of two materials, like say copper or a diamond, is to see which one scratches the other. So if I take diamond and I rub it against a copper sheet, you'll see that the diamond scratches copper. But you can't use copper to scratch a diamond because a diamond is harder than copper. And in the picture you can see that an artist has obviously taken advantage of the fact that copper can be scratched easily and has scratched artwork into this copper sheet, which I think is pretty cool. And for several years, diamond has been considered the hardest material on Earth. However, over the past 6 to 7 years, there have been a few discoveries where people, scientists working in laboratories, have claimed to have found, at least theoretically, other materials that are stronger than diamond. But I should mention this, that on a lot of online resources, like if you go to the Wikipedia page, it still states that diamond is the hardest material known to man. But just recently there have been some big discoveries claiming that they have found materials that are stronger than diamonds. Just watch this video clip to see one of those examples.
Two Russian-born scientists shared this year's Nobel Prize in Physics for experiments with a substance they discovered in 2004 called graphene, the thinnest and strongest material on Earth. A layer of graphene is a single atom thick, so tiny it would take more than 1 million sheets stacked on top of each other to reach a single millimeter tall. But if you stretched a sheet of the carbon-based chicken wire-shaped material over a coffee cup, it would be strong enough to support the weight of a car. Scientists think that in the future, the wonder material could be used for high-capacity batteries, flat-screen TVs, and for ultra-small computer chips, its most promising use. And despite its amazing properties, graphene isn't rare. In fact, anytime you write with a graphite pencil, graphene is produced. That's how it was first isolated by prize winners Andrei Game and Konstantin Novoselov, who used Scotch tape to collect graphene from pencil lead. Which just goes to show you don't need a lot of money to win a Nobel, and almost none to win an Ig Nobel, the yearly prize for the least distinguished scientific research. Past winners of the Ig Nobel included a Welsh scientist who invented a high-pitched noisemaker designed to scare away teenagers, a researcher in Australia who studied belly button lint, and one in sociology for a PhD student who wrote his thesis on Canadian donut shops. In 2000, one of the Ig Nobels went to a scientist who levitated a frog with a magnet, whose name was Andrei Game, who 10 years later became the first individual to win both an Ig Nobel and a real Nobel when he shared this year's Nobel Prize in Physics for pioneering research on graphene, the world's strongest material.
Another physical property that we need to talk about before we conclude today's lesson are melting points and boiling points. Now, these are pretty much common sense, so I'm not going to make you watch a video on this physical property, but just know that the temperature at which a substance changes from a solid to a liquid is its melting point. If you look at the picture to the right, you'll see liquid gold. So gold has a melting point of 1064.2 degrees Celsius. So you typically think about gold being a solid, but once it's heated to this temperature, it becomes a liquid and can be poured just like pouring water. Now, boiling point is the temperature at which a substance boils. This is called the boiling point. So when it goes from a liquid to a gas, and you guys are probably familiar with this, but the water boiling point is equal to 100 degrees Celsius. The important thing to remember, though, is that melting and boiling points are considered physical properties. And finally, we have density. So density can be used to test the purity of a substance. Now, don't focus too much on what density is. I just want you to focus on the formula. This formula will be provided to you on your test, which is this Thursday. And it's just a simple mathematical calculation. If I give you the mass of something, you just plug it in for mass. And if I give you the volume of a certain material, you plug in the volume. And then when you do mass divided by volume, you get density. So you'll usually see this formula as D equals M over V. So That concludes today's lesson. Just go through, pull up the in-class notes in iTunes U, these slides, and you will see 2 practice questions. 2 questions about density, which is you have a rock with a volume of 15 cubic centimeters and a mass of 45 grams. What is its density? And then the next one, you decide you want to carry a boulder home from the beach. I'm not sure why you would want to do that, but it's a good problem. It is 30 centimeters on each side, and so has a volume of 27,000 cubic centimeters. It is made of granite, which has a typical density of 2.8 grams per cubic centimeter. What's the mass of this boulder? I want you to go ahead and try these 2 practice problems as homework, and then bring them in to class tomorrow, and we will discuss how to calculate the densities of different materials, or how to use density to calculate something else like mass. All right, I hope you enjoyed this lesson. You guys have a great night. Bye.